Hello everyone and welcome back to another video. Do you actually want to know how quantum computers can change the industry, what applications are relevant and how the algorithms are going to impact, or the quantum computers are going to impact different applications? Then today's video might be exactly the right one for you, because today we are going to take a look at a company called ColibriTD. And with that, let's hop right into their website and discover what they have to offer. So here we are on the website of ColibriTD, and it says revolutionizing multi-physics simulation with quantum computing. And then here we see the interface. So this time we see that it's on the software side, on the algorithm side, and it says here explore quick apps. So we will later on learn a bit more what quick actually is. And then you have the applications here, view your quantum hardware usage, so which quantum computers are you using and how much are you using them, and then previous simulation, climate modeling, welcome back, yada yada. And then discover quick. But before we discover quick, let's actually just scroll down and see what else we find here. So it says quick quantum innovation computing kit. That's probably the acronym. And it says hardware agnostic, so runs across multiple quantum backends and integrates into classical pipelines. And we have seen other platforms already that integrate with different of these providers, right? So there are already, let's say, pure software ecosystems that enable you to access quantum computers, but there's other stuff coming here on top of that. So seamless integration designed to plug into existing tools and workflows used by engineers, then built for industry, so validated on physical quantum hardware with real engineering use cases. And that's, I think, how I understand is the focus here. So it is focusing on building real use cases that are industry relevant. Then it says universal, so able to address all types of engineering simulation problems from semiconductor to finance. And I think looking up here, there's going to be use cases which we can learn about. There's multi-physics, so designed to handle multi-physics problems by default without trade-off between realism and speed. And then finally, there is the linear scaling part, so efficient scaling with number of variables and complexity of the problem. So one quick note here, designed to handle multi-physics problems by default without trade-off between realism and speed. That is probably also something that's going to be interesting to understand a bit better as we move along with this analysis today. So they trust us, trusted by industry leaders for quantum computing solutions. And then we find a couple of names here like Eviden, Early Bird, there's AWS, IBM Quantum, and many, many more. You already see that there is like BPI France. The company is also based in France. On top of that, we find here a couple of frequently asked questions like what is a quantum computer, what are qubits, how can quantum computing change the world, how long will it take to learn quantum computing, is quantum computing a good career, why is quantum... Let's see what the answer to that one is, just for interest, right? We're also here for the fun. If you have a strong background in physics, computer science, mathematics, or a closely related field, quantum computing can be a very fulfilling career choice for you. There is currently a lot of need for engineers and developers in quantum computing in the fields of artificial intelligence, software development, and even healthcare. The quantum computing industry is quite large and continuously growing. It's the perfect time to take the next step in your career and join the quantum revolution. For open positions, especially at ColibriTD, take a look at our, and then I guess here it says careers page. Quick note on that also, when I finished university, when I finished with my PhD program, the landscape was indeed a very different one. So there were not so many companies already out there. There were a couple of startups in the, let's say, quantum technology space, maybe not so many on the quantum computing side, but also other quantum technologies, and only a very couple of big players, mainly outside of Europe, and were actually working on quantum computing, which made it kind of difficult to get a step in, and also it was still kind of easy it was not easy to understand the market. And that's also kind of motivation of making this video series, to show you what else is out there, how many opportunities there are, what new companies are on the way towards this quantum industry. So yeah, if you struggle from the same problem, you are, let's say, working in quantum physics, you are interested in staying maybe even in this space, and that was also one idea that I had back then in my mind, besides of course also exploring other spaces. There was this idea of maybe I can stay in that space even, because it is interesting, it is dynamic. But I think there were not so many opportunities. Now, and I'm recording this in early 2026, I think we have the year with the highest invest in quantum technology behind us, so 2025. And of course, all of that money needs to also go somewhere. And of course, you buy equipment, you develop technologies from that, which is expensive, but you also need people, right? So I'm expecting that there's going to be quite a high demand for new people joining. And as this kind of technology field is growing, and I mean sensing, communication, and quantum computing, you see that there will be a need for more people joining this from different backgrounds, not only engineering, which is also a reason why I'm making this series, for you to kind of see what companies are out there. Okay, but what else do we have? Why is quantum computing useful for optimization problems? Is the quantum industry diverse? Is quantum computing secure? What is quantum computing? What is the fifth industrial revolution? How is quantum computing used in machine learning? How do I learn quantum computing? And how is quantum computing used in drug discovery? And these are all very good questions. I'm not going to go, for the sake of time, through all of these now. Let's quickly check out what solutions what the solutions are being offered. I'm not sure what is happening here. Somehow it's not opening those. Maybe there's something off. Let's try to open it in a different tab and see what is gonna happen here. I don't know what's happening here. Sorry for that. There we are. Probably something on my side. Okay, here it says quick discover our quantum solutions, quantum innovation computing kit quick. And then again, as we saw before, hardware agnostic, seamless integration, and built for industry. So the acceleration of scientific discovery is capital for many companies, but quantum tools remain limited to very few entities. At ColibriTD, our mission is to bring these advantages to everyone with the help of our experienced quantum experts. We believe that making quantum computing tools accessible to everyone can not only speed up scientific discovery, but to change the landscape of research and development as we know it. The Quantum Innovative Computing Kit, or QUIC, provides our customers with technological, financial, and environmental excellence in a software platform that runs your use cases in the best available hardware at the lowest cost and the optimal energy efficiency. It's a plug-in that can be integrated to establish simulation software. This can be used, for example, to model physical systems, streamline manufacturing, and to find new designs for engines. To power QUIC, we built HDES, the Hybrid Differential Equation Solver. It's the engine at the heart of our platform, combining spectral methods with quantum classical optimization to solve complex PDEs, so partial differential equations, efficiently and at scale. To make HDES accessible to a wider audience, we released QUIC PDE, the first implementation of our solver available for developers and researchers. QUIC PDE brings HDES to life through a simple, ready-to-use interface that runs directly on IBM's utility-scale quantum computers. It's featured in the IBM Qiskit function catalog, a curated collection of pre-built quantum functions that make it easier to develop, to integrate quantum capabilities in their workflows. With QuickPD, users can already solve meaningful multiphysics problems such as Weissenberg's equation for fluid dynamics and hypoelastic 1D deformation for solid mechanics, paving the way for broader adoption of simulation in engineering and research. Okay, that was a lot. Let's quickly take one step back and go through it step by step. So, hybrid differential equation solver. Differential equations are equations that more or less describe systems, for example, from a mechanical point of view. So if you have, for example, a pendulum, you see that the pendulum is kind of swinging back and forth. And this swinging motion can more or less be described by a differential equation. And actually, a lot of problems or a lot of things that we observe in nature, they are in fact described by differential equations. You could, for example, also think about a water bubble or a water drop that is falling down, and actually the shape of this drop is described by a differential equation. So these equations, they not only play an important role in let's say how nature is actually working, but they are also extremely interesting for engineering properties. And that includes, of course, engineering of, designing a car, but it also includes other stuff like using that to simulate chemical reactions and things like this. And these partial differential equations, so the PEDs, so of complex PEDs efficiently at scale, so the partial differential equations are a part of these differential equations, so a class of those. There are many, many more different types. Some of them play mainly a relevance, I think, in the world of mathematics. Other ones are more important in physics. Partial differential equations are typically a type, a category, a family of differential equations that you find in physics-related problems or in physics descriptions, like in what nature actually does, right? And then these spectral methods here, they are basically a way of solving, I would say, these equations. So combining spectral methods with quantum classical optimization to solve these differential equations at scale. And that's basically what this PED is doing. So that's this method, and it has been implemented into a program language already that is running on IBM's quantum computers, which is called Qiskit. So Qiskit is the language at which quantum computers from IBM can be programmed, but in fact, actually Qiskit is an open source language, so it is available to everyone. And other manufacturers of quantum computers have also integrated this already. So if it's available in this language, you can probably also run it on other types of machines that understand Qiskit. So that is kind of the let's say, break apart of this explanation here. And then I guess this, for example, hypoelastic 1D deformation is probably some type of problem, deformation problem, like, I don't know, you have a wire and you pull on it, that can already be mapped and described using this method. So our vision for our Quick platform, Quick brings together classical performance and quantum innovation, shaping a new era of simulation for industry leaders. Here's what's coming next. So Quick CFD, dedicated to advanced fluid dynamics, turbulence modeling, and multi-phase flows. Then Quick MD, built for solid mechanics, stress strain analysis, that's what I just meant, right? Like pulling stuff apart, and nonlinear material behavior under extreme conditions. Quick Finance, focused on PDEs, partial differential equations, right, for risk modeling, option pricing, and stochastic processes. Quick Structure for mechanical and structural analysis, including vibration fatigue simulation, right? This is what you want to look at when you, I don't know, design bridges, design stress tests for objects, for systems, for buildings, whatever, right? Quick thermal, designed for heat transfer simulations, thermal management, and coupled thermomechanical behavior. Quick electromagnetism, tailored to pave propagation, radar scattering, antenna modeling, and electromagnetic field interactions. And I mean, all of that kind of makes sense, right? Thermal is, at the end, thermal properties of materials, they are more or less set by quantum properties. And if you take a lot of small quantum systems and you combine them stochastically, then you end up with the thermal properties. So you can actually derive quite a lot of thermal properties of materials by just taking the quantum system and running statistics on it. So say there's infinitely many of these systems and they all have a little bit different behavior. That's what temperature is, right? Some of them vibrate a little bit more, others vibrate a little bit less. And if you do statistical analysis on that, that's what temperature is basically giving you. So for the physicists, it's like broadening the Fermi levels and stuff like that, right? Like broaden the Fermi smear out. Electromagnetism also makes sense, right? If you want to look at small systems and see how waves are propagating, like for example in radar and antennas, that makes sense. That is something that is already, of course, also being done. All of this is already being done in classical machines. Then there's quick combustion, dedicated for reactive flows, flame dynamics, and coupled thermochemical simulations. The quick set solver, designed for large-scale constraint satisfaction problems and complex combinatorial optimization. So I guess this is like logistics. And the quick supply chain optimizer, focused on dynamic network optimization, demand forecasting, and resilient logistics planning. So that's also the logistics space. And I mean, if you take a look at those and you take a step back, you will see that actually, from my point of view at least, these problems that you see here, they were also the first problems that were being run on, let's say, the first supercomputers, right? So when the computers actually started and companies invested into that, the first things that they've been doing is exactly solving these kind of problems. So there was of course in the time where like what our smartphone can now do in our pocket was still requiring halls full of, let's say, systems to run those calculations. But indeed, at least for example, if you look in Germany, the car manufacturing, the car industry used actually these types of computers to run these types of material simulations and things like that. So I think there's a certain parallel here to how the classic computer revolution, at least in the manufacturing space, looked like and what the quantum computers are now doing, or maybe going to do, right? So our goal is to make module accessible directly via our platform or through IBM Quantum as a Qiskit function, enabling industries to move seamlessly from classical to quantum workflows as hardware scales. Experience faster and more efficient computing with our quantum computing solution. And then, of course, there are the other solutions that we've seen before, right? Like the differential equation, hybrid differential equation solver. So the first PED solver worldwide at ColibriTD. We are the first in the world to have solved a partial differential equation on a real quantum hardware on IBM Heron 156 qubits using 50 plus qubits. In addition, we are the first IBM Qiskit function for solving partial differential equations. And there you can see the function. And then with that comes what we've already seen before. Here's something that is new in this context. So variational quantum algorithm, VQA. We have talked about this a little bit in the series before. So this is sometimes also considered to be, I don't know, some people would maybe call it AI or machine learning or whatever you want to call it. But at the end, it is set out of this hybrid quantum classical loop. So you have a classical computer that is running some optimization that is then being probed or deployed on a quantum computer that makes use of this Hilbert space, so this highly dimensional system, to run some type of optimization. And I'm not an expert on that. To me, this is a heuristically interesting thing. So people are trying around with that, and there's also some results on using that already, and some interesting studies on that. But at the end, what you do is you have your input with the boundary conditions, and then you basically run it in this variational quantum algorithm ansatz. So you basically start with your circuit, so that can be like running certain types of gates, and then the gates, they usually have some functional parameter. Let's say, think about very simplistic example now. Think about a spin qubit, or like some qubit that has a state 1 and a state 0. And you can now tilt this at a certain angle. And this angle could be a function, could be a parameter that you want to tune in order to describe some type of function. And then you perform your measurement. So measurements, expectation values of observables. You have your loss function, so you compare the output to the output that you would want to have. So that's the machine learning part, right? More or less. And then you run your optimizer on your classical system as you do it already today with neural nets and whatever. You tune this parameter, in this case the angle, and then you run the same type of thing again. And that way you are training this function, which in my case only has one parameter, which is this one angle, to kind of approximate the function that you actually want the machine to learn. So at the end you would get your trained model that is running on a quantum machine. And of course, if you have many gates and you create entanglement, you can go to higher dimensions, right? Because suddenly one angle is becoming entangled with another angle because you're running some type of entanglement gates between those. And suddenly you are coming to this, let's say, more complex system. So what is a VQA? Quickly going through that. A variational quantum algorithm is a hybrid algorithm that combines quantum circuits with classical optimization to solve complex problems more efficiently. This is especially suited for today's quantum hardware NISQ device, which is still noisy and limited in size. So NISQ is noisy intermediate state quantum devices, I think. So noisy and limited in size. VQA is built from 4 key components: an ansatz, a parameterized quantum circuit whose structure defines how the algorithm explores possible solutions. So this is like how you actually combine these spins, which ones, or not spins, the qubits, and which ones you entangle with each other, which gates you're running, right? Then the encoding step, a way to translate a physical, mathematical, or industrial problem into a quantum state. Then you are running the cost function. This evaluates how good a candidate solution is, guiding the algorithm towards the optimal result. And then at the end, the classical optimizer, a traditional quantum computer that adjusts the quantum parameters step by step to minimize the cost function. And then the quantum circuit proposes a solution. The classical optimizer improves them, and both work in a loop until convergence. And that is this loop which we are seeing here, right? So why are these systems so powerful? VQAs are designed for the quantum computers we have today. They use shallow circuits which make them compatible with NISQ hardware, and they naturally handle noise better than many traditional quantum algorithms. Because they can adapt to different types of problems, VQAs can act as a general purpose solver, including, for example, simulation tasks such as solving PDE-like multi-physics problems. A quick point on the noise part. That is, of course, in an ideal quantum computer, so an error-corrected one, you will not have any noise anymore. But in order to create such a computer, you need many physical qubits, which you can then run an algorithm on, making them a logical qubit. So this is the idea of this error correction. Now, since we don't have so many qubits yet, mostly the computers, the machines are not running these kind of error correction algorithms. The first ones that we've actually seen in action were last year in 2025, but still this is very early stage. So what we have for now and what we will probably have for the next couple of iterations of systems will be this NISQ type of hardware, where you have physical qubits that you are acting with. They have certain errors in them. They do certain things wrong. They collect these errors over time. Now, why is the VQA actually still interesting in these systems, or why is it even maybe good for these systems? Because actually your optimizer is optimizing out these errors as well, right? So you're putting in some data, you're running it on the quantum computer, and if it now creates some errors in there, and you then compare it to the final result, it has to learn to kind of mitigate those errors in a way. That's a little bit like when you're looking at machine learning and you have these denoising functions now, where you have like an image which has a lot of noise in it, you run it through the AI, and then it gives you something that looks less noisy at the end. This is the same thing. It is not always correct, right? It doesn't necessarily, in this case, always correctly filter out the noise, right? So you have to have some way to kind of check things back at the end, but at least you can train it and the results, they look plausible. So I think the same thing more or less applies here. So the system will learn the intrinsic errors, try to filter them out, probably most of the times actually succeed in doing so, and then you can run some interesting problems already on those systems. Okay, then there's something which we haven't seen so far. This is this multi-platform quantum programming MPQP library. I think this is what kind of sits on top, right? So it says MPQP is Colibri's open source library designed to bridge the gap between classical high-performance computing and emerging quantum architectures. Built to be modular, interoperable, and hardware agnostic, MPQP allows developers, researchers, and engineers to design and run hybrid solution workflow across CPUs and quantum processors, all within a unified programming interface. At its core, MPQP abstracts the complexity of back-end specific quantum SDKs, so software development kits like Qiskit, Bracket, or Cirq, which are basically other options to Qiskit, for example from Amazon, and let users to focus on what truly matters, simulation. Whether you're prototyping a new algorithm, optimizing PD solvers like HDES, or connecting your industrial simulations to quantum resources, MPQP is the foundation that keeps your code portable, scalable, and future ready. You can start exploring MPQP today by visiting our GitHub repository, where you will find the code contribution guide and installation instructions, and our online documentation for detailed examples, API references, and tutorials. Whether you are a researcher, educator, or developer, MPQP is designed to help you run, compare, and experiment with quantum algorithms across more easily. As always, if you want me to try this out, please let me know down in the comments below, and then we can make a video about this. We can check it out together. We can maybe even do a little course all together where we kind of explore this programming interface. And there are access ways here for academics, for companies, and hopefully also for us, where we are kind of a little bit in between, I guess. Good. Let's quickly go into the use cases section. I don't want to go through all of these to not make the video too long. We know a little bit about finance. I think defense is a bit of a new one. Aerospace and automobile we've heard before, energy we've heard before, and semiconductors is probably also a bit of a new one. So let's maybe take a look at defense and then also jump into semiconductors as well. So defense, quantum ready simulation for strategic advantage in defense, precision, reliability, sovereignty. Modern defense systems depend on physics-driven models, from aerodynamics and materials to electromagnetic propagation and thermal management. These models rely on partial differential equations, PDEs, that are computationally intensive and demand extreme accuracy. With ColibriTD's hybrid quantum classical platform QUIC, defense innovators can explore how quantum computing will enable faster, more precise, and more sovereign simulation capabilities, securing technological independence in critical domains. So important also here, because there's also a lot of hype, right? It says can explore how quantum computing will enable faster, more precise, and so on, right? It's not that we have this advantage yet, but it will if the quantum computers are actually scaling the way that we are hoping they will, right? So quick navigate through the use cases, electromagnetic simulation and radar stealth. So this is the electromagnetic part, which is related to radar, ballistic and structural dynamic modeling, and wave propagation and atmospheric phenomena simulation. So I guess the first one is kind of clear, right? Electromagnetic simulation and radar stealth. So stealth is when you try to not appear on somebody else's radar. So I guess that one kind of makes sense. Ballistic and structural dynamics modeling, I can also probably understand. So let's quickly jump in here. Simulation, impact, penetration, or detonation events involve solving nonlinear multiphysics partial differential equations that couple mechanical deformation, thermal transfer, and fluid dynamics. Traditional solvers often struggle to maintain precision and stability under these extreme transient conditions. So this is about, let's say, impact, right? Like physical impact. And then wave propagation and atmospheric phenomena simulation, understanding how waves, acoustic, seismic, or electromagnetic, propagate through complex or changing media is essential for surveillance, communication, and guidance systems. These phenomena are governed by propagation PDEs that become extremely demanding in realistic, turbulent, and or variable conditions. So this is about, let's say, intelligence-related topics, I guess, as far as I understand. Good. Then also jump into the semiconductors really quick before we come to the company itself. So Semiconductor is quantum-ready solution for next-generation chip design. As semiconductor technology pushes below 3 nanometer nodes, designers face growing challenges in accuracy, speed, and scalability of simulations. From power integrity to thermal effects and migration, these problems rely on complex PDEs that quickly exceed classical computational resources. With ColibriTD's hybrid quantum classical platform QUIC, semiconductor engineers can accelerate multiphysics simulation, detect anomalies early, and optimize chip design, preparing for quantum-enhanced semiconductor modeling. And then there are also 3 examples here again. So early anomaly detection in microchips, then thermal and electromagnetic migration modeling, and then advanced power and signal integrity analysis. So early anomaly detection in microchips. Traditional IR drop analysis struggles to balance accuracy, speed, and scalability. Full chip simulation can take days to weeks, scaling cubically with circuit size. This sometimes missing worst-case watch scenarios problem that worsens as transistors shrink. So that has to do something with how the transistors actually work, the inverse subthreshold slope, and kind of how much you can deplete the channels with the gates, and how the doping actually works at these very small scales. There's a lot of details to that, which we are not going to go into. But I think what is clear is Moore's law is telling us that the number of devices still does, or maybe has, kind of exponentially scaled. So you need to exponentially have more and more of these transistors simulated, and then you can also stack them in the chips on multiple layers, leading to this three-dimensional or cubic scaling of the systems, which makes it more and more difficult to actually simulate them properly. And the statement here is, because of that, people skip out on certain steps because it will just take too long. And then that can lead to some issues, to anomalies. And the idea is that here, okay, we are using these methods to actually detect these anomalies later on with quantum computers on scale. Thermal and electro migration modeling. So as transistors densities increase, localized heating and current crowding create thermal hotspots and electro migration risks. Threatening performance and lifetime. So that, I think, has to do something with if you have electrical fields, you can move charged particles, like for example ions. If you think about a semiconductor, you have these doping ions in the silicon crystal. And if you now, usually they are fixed in a position, but if you now apply high voltages and you have high temperatures, they can actually start to move because things are shaking. And then you can actually move them, or you can move things within the crystal. And that, of course, changes the properties of the system. And that is something that you want to be able to simulate, because that affects the lifetime of your system, right? Because at certain temperature, like the higher the temperature, the more movement you have, and the quicker the deterioration of your overall system. Okay, and then the advanced power and signal integrity analysis. So high frequency circuits, multi-core processors, and complex IC architectures require precise power and signal integrity analysis and under dynamic conditions. Classical methods struggle to simulate large-scale interactions quickly, and the idea is, okay, here you can simulate that. Like the high frequencies mean very dynamic situations where the voltages are quickly changing, so you're not able to model that in a constant system and then just do the time propagation, but here it's like the system is continuously changing. So you have to simulate much more, I guess, interactions per time scale. And therefore, I guess that's why you also could profit from this in the future. Okay, let's quickly talk about quickly learn a little bit about the company. So empowering enterprises in the quantum era. ColibriTD, we are, I think it says just can't see it because of this block. At ColibriTD, we are on a mission to transform the business landscape through accessible quantum computing technology. We firmly believe that by harnessing the potential of quantum computing, enterprises can unlock unparalleled value and gain a decisive competitive advantage. If you're considering becoming an investor, partner, or joining our team, know that you're stepping into a realm where innovation meets opportunity. Together, let's pioneer the future of business. And then here we see the team of the company, who we are. ColibriTD is a deep tech company revolutionizing industrial simulation through quantum computing. Founded in 2019, we develop hybrid quantum classical technologies designed to accelerate multiphysics simulations. Our flagship platform, Quick, and our proprietary algorithm HDES empower industries to simulate complex systems with higher precision, reduced computational cost, and seamless hardware flexibility from HPC to real quantum processors. Building on years of research and collaboration, ColibriTD achieved a major breakthrough by becoming the first company to run a PDE solver on a real quantum computer, leveraging IBM quantum technology. This milestone paved the way for the launch of Quick PDE, our first Qiskit function available through the IBM quantum platform, marking a new step in the integration of quantum simulation into industrial workflows. And this is just the beginning. We continue to advance boundaries for hybrid quantum classical simulation, bringing the next generation of computational physics closer to real-world applications. One thing that probably sets them aside a little bit from others is here the focus is not on enabling access to quantum computing machines. I mean, that is of course part of the proposition, but as far as I understand it, or how I understand it looking at it, is there's this core invention which is this way of solving partial differential equations, and this HDES type of approach, algorithmic approach, that is sitting, let's say, at the fundament of how the company kind of works. And then they are looking, okay, how can you actually apply this to different types of applications from industry? And that's what we've been seeing here in those use cases. These are applications that the team is thinking, okay, they could be interesting for the industry. And that is kind of how it is being structured. So that is kind of the full stack. And it's not about, let's say, enabling access to all types of quantum machines that are out there, but more like coming from the algorithmic side. We have this solution, we have invented this algorithm, and then kind of connecting both the application and the underlying layer, which is the compute, and kind of drawing this line, which is then creating, of course, on the algorithmic side, the value chain. The story, so the name ColibriTD comes from the fusion of two founding ideas, Colibri and ITD. What began as a shared vision between Hannes and Lauren to make quantum simulation practical and accessible, probably Laurent, has evolved into a company bridging the gap between research and industry. With several scientific publications, real-world industrial projects, and European innovation projects, ColibriTD continues to push the boundaries of computational physics. Our values, ColibriTD, our values are foundation of how we build, collaborate, and innovate. And then here you see the values, which are collaboration, autonomy, scientific integrity, and then impact through innovation. And then looking ahead, we are building the foundation of the next generation of industrial simulation, on where quantum computing becomes an everyday tool for engineers, researchers, and innovators. Our mission remains clear: to revolutionize industrial simulation with quantum computing and make it truly usable by everyone. And then we end by quickly taking a look here at the team. So you see the two founders, I think, that were mentioned before as the CTO and CEO, and then a team of people with, I think, scientific acumen. So you see a lot of PhD backgrounds here. I think they all have some kind of background on the scientific side, as far as I see it here, if I look at it. So they're all really experts in, let's say, the quantum simulation part. ColibriTD numbers. So let's see, what do we have here? Currently, there are approximately 70 quantum hardware providers offering various qubit technologies. Simulation require finite grid as 20 to 30 high quality qubits, a single solution linking to the 70 plus available quantum computers. And then I guess that's it. So with that, I thank you very much, as always, for joining me in today's little adventure of exploring ColibriTD. If you found this interesting, and if you haven't seen the other videos yet, then go check out the channel, because we have a whole list of all of these hidden quantum champions that you might have never heard about on the channel, and we feature them. If you don't want to miss out on the next one, as always, make sure to subscribe to this channel and always stay hydrated. See you in the next one. Bye bye.